Alright, so this is we're going to start talking about inductance and an electronical component called an inductor in a circuit, kind of explain what inductors do. So let's say we have a coil of wires. What coil of wires do are produce constant magnetic fields that point in either a direction down the coil or the other way down the coil. So perpendicular to the direction the coil is. Perpendicular to the direction the loops in the coil look like they go. So in the direction of the cross-sectional area of the coil. Now the units for inductance we define as henries, and the way we define inductance is by doing number of loops of coil times the magnetic flux divided by L. Essentially what inductance is really measuring is a way of measuring the effect of current in one loop of a coil on magnetic flux in all the other loops of the coil, is really what it's measuring. Now, an inductor is any type of electrical device that is made up of coils of wire that create magnetic fields or changing magnetic fields. So let's look at a solenoid, and basically what a solenoid is, if you remember, it's a long, it's kind of a spring or a slinky, a set of coils of wire that those loops of wire are separated by some distance L. Here we have a solenoid that's number N turns in length L, a cross-sectional area I, and we're passing a current, or A, for my cross-sectional area, and passing a current I through the solenoid. Now let's see if we can figure out the inductance of the solenoid. So inductance is number of turns times magnetic flux divided by current. So it's really related to the total flux through all the coils as a ratio of the current going through the coils. Now, flux, if we remember right, should be magnetic field strength times A. And here we know that the A vector and the magnetic field vector are going to point either in exactly the same direction or exactly opposite directions. We could set it up so they point in exactly the same direction. The magnetic field for a solenoid, we also know. Number of turns times mu naught times I divided by L, the length. Or really, number of turns per unit of length, what I call little n, mu naught times I. Now if I substitute all of that in for magnetic flux, I get mu naught n squared I A over IL, and the I cancels out. So really, the inductance of a solenoid is independent of the current. Now if we do one more step here, we can say that it's equal to mu naught times n squared, number of turns per unit of length times area. And so really the values that determine the inductance of a solenoid are really how spaced the coils are. That's the little n, number of turns per unit of length. The total length of the solenoid, that's the L, and the cross-sectional area of the solenoid. So next let's look at an inductor and look at how an inductor, or what an inductor actually does in a circuit when it creates a magnetic field, or as it induces a magnetic field. So what we have in this inductor is normally we have a magnetic field strength, or a magnetic field that is going in that direction. You can actually show by the right-hand rule the magnetic field points to the left in this inductor. Well, if you start to increase the current, you're increasing the flux that is produced in that direction, which will induce an EMF on all the coils which oppose that change in flux. And so what that would really do is it would induce an EMF in the opposite direction of the current. So it'd try to prevent you from changing the current in this circuit. Now if you're trying to do the opposite, decrease the current, well, you're going to get a magnetic field that gets induced the opposite direction. Well, decreasing the magnetic flux induces a current, an EMF, in the same direction as your original current. And so in that direction. So really what an inductor does is it resists the change in current in a circuit. So it tries to slow down changes in current. So let's look at induced EMF in an inductor and see if we can calculate that out. If we say inductance is N times flux divided by L, well, we could rearrange this as L times I equals N times flux. Well, the EMF should be equal to d dt N times flux. Well, I know N times flux is the same thing as saying L times I, right? And so if we plug that in, since L should be constant, we get the EMF of an inductor is L times di dt. So really related to the rate of change of current tells you what the EMF induced in the inductor is. Now it's worth pointing out this EMF induced in the inductor you could use in, say, Kirchhoff's rules. If you put in an inductor in a circuit with a resistor, which we'll see coming up, we can look at what happens in those types of circuits. Or what happens in a circuit when you have an inductor and a capacitor together. So there happens to be some magnetic field or energy that's stored within the magnetic field of an inductor. This energy stored in the magnetic field of an inductor looks similar to the energy that's stored in the electric field of a capacitor. And we can actually work this out to figure out what this is. Now notice I've dropped the negative sign. Really what the negative sign is really telling me is directions of things. That it's the opposite direction that the change in current is going. Now if we say du dt, well, remember that U should be voltage times I. VI equals power, and power is really du dt, change in potential energy. So we could call it Li di dt. Well, if we multiply everything by the dt's, they cancel out, and you end up with du is equal to Li di, which if you integrate it, you end up with half Li squared is the energy stored in the inductor. Now, if we wanted to calculate the energy density, we take that and divide it by 2, or we take your magnetic field strength and divide it by 2 mu naught. Now, it's worth pointing out, if you go and look at the energy stored in a capacitor, I believe you get half CV squared. You get a very similar argument or a very similar type of calculation when you calculate that out when you go to calculate the energy stored in a capacitor. So there's a few things about inductors. We'll look at in kind of the next set of lessons are, what if you have two coils of wire that you're changing the current in one and seeing what happens in the other one, and then what happens if you start to put inductors in circuits with other components.